Thanks, Bob. Sent me a nice coffee mug here. And Jack, who also sent me something I can use. 11th All Z80 assembly language programming book here, complete with properly worn edges and everything else. I mean, I wouldn't want a brand new one. People would think that, hey, I'm just warehousing stuff down here instead of actually using it. Thank you very much. And thanks to all my Patreon subscribers and thumbs uppers and viewers. You really help out cover the costs of these hobby projects and keep this whole thing going. Thanks. Remember, I have modified my retro BIOS to factor out the I/O routine so that we can pick which library we want. The one that we've been using all along is the non-cached version, or we could call that a one-slot cache. It's commented out, and I commented in my direct map cache version here. And I want to go over this, make sure everyone knows the state of this, because this is not what I have committed to GitHub. These are the differences between what's in GitHub and what we're talking about in this video right now. The reason this is not in my GitHub is because this doesn't work. We're debugging this. It has read support, but no write support at the moment. And I wouldn't want to confuse somebody who's made one of these and can't figure out what's going on if they grab the latest and greatest stuff. So the latest and greatest one that's committed is still the one that has the single slot buffer in the BIOS, okay? What are the other modifications I made? I turned on debugging so that we can dump out more stuff. And I have the wedge that I talked about last time turned on in my console routine. Okay, so this is about then the direct map cache support for the BIOS SD card read and write routines. Talked last time, I added a bunch of doc and stuff in here to make things clear what's going on and have the debug of this module turn up to the max. And we're talking about the debug a lot and the basics and all the background, how things all map together and how the track turns into slots and so on. And all these little routines in here. Okay, so we're all set to go. This time we're going to wrap up the read routine here. Okay, I've already talked about all the debugging that's going on up here to make sure that everything matches the design intentions, to make sure that all these little subroutines that we wrote work correctly. Okay, and we finally get down to the actual logic again. Well, what I've done here is I've taken the read routine that we already know and love. From the first draft of the BIOS that actually works. It just directly talks to the SD card, and I've modified it to insert all these little subroutine calls to work with the SD card's direct map cache logic here. The main read logic starts the same as it always did. We create our local stack because we need more space than we get by default from the BDOS. And I talked about this when we went over the SD card driver and stuff like that. It just needs too much stack to function with the, whatever it is, 7-level stack that we get from the BDOS. Save some registers that we might use in here. Originally, I wanted to make sure that I could call this from the warm boot logic that we've talked about before, without this messing with too many registers, so that this logic here could work a little bit more cleanly. But honestly, this probably was a misguided effort here. I'm leaving it in for now so I don't have to mess with anything else. But yeah, at some point I probably got to clean that up, as well as a few other things that you might notice as we go along. So what do? I use the little routines I wrote. I'm going to take the track number. As you recall, the track number is the root of all that exists in this cache logic. We take our track number. We can directly translate that into the tag that belongs into the tag table simply by using the most significant byte, which is fairly straightforward. That's why direct map caches are direct map, directly mapped into here. And the least significant byte is directly used as the slot number that tells us which one of the tags in our table and which one of the slots in our cache this track must be placed into if I'm going to store it in my cache. I also use the slot number directly like this to figure out which RAM bank the slot data is actually stored in. And I use the rest of the slot number bits after shifting them over like this to represent the address of the very first byte in the slot that is stored in this bank based on this slot number as a whole. that's not really obvious, go to the description below this video on YouTube and look for the other parts of the cache discussion where I go over all those details. So the bottom line is you'll see me repeatedly grabbing the BIOS track number that we want to read. The BIOS wants data from some track, actually more specifically a sector that's on a track, but the cache stores whole track images. So most of the all the cache logic and the banking logic will be based on the track. So I translate the track to a slot, the slot to the bank number, and this subroutine returns the bank number in the accumulator, and I then transfer that into the D register. As you recall, the bank from this subroutine is returned in the form that looks like this. The bank number is not just stored down here in the least significant bits. It doesn't really translate it to a bank number per se. It translates it to the bank number that's been multiplied by 16 and or shifted left by 4, however you want to think about that. This represents the bit pattern that I need to store in the GPIO latch in order to select the bank that holds the slot that I want to interact with. Okay, so that function is set up solely to create this thing, and I store that in the D register because I'm going to use it a little bit later down here, and I'm going to store that into the GPIO latch to turn on the bank I want. Now, before I do that, what else do? I grab the track number again. Granted, this could be optimized a little bit, but it's for readability and discussability right now. And if you actually run this and do some timing tests, you'll see this is much faster when the cache is actually being used than the older version. So even if this is a little bit inefficient, that's probably not a problem, especially if it's easier to understand. For now, that's my goal. All right, so I get the bank number, and I salt it away in the D register. I then go back and I translate this track to a slot, and then I convert the slot back to a track again, which may seem a little bit illogical, but keep in mind which tracks we're dealing with. This is the track that the BDOS wants to read. I convert that to the slot in my cache where I know that track has to be stored if I actually do read it, and or if it's already in the cache, there's only one place for it to go because I got a direct map cache, and that would be in this slot. This routine over here says, given a slot number, tell me what track is currently there. So that later on, and we'll see that down below here, we can then ask, is it the one that I want to use right now? Because more than one track can go in the same slot, right? If you look at the track numbers, any track that ends with, let's say 00 or 01 or whatever, all has to go in the same slot because the least significant byte of the track number is the slot number. The most significant byte of the track could be anything. So we could have up to 64, because these bits aren't used, different tracks, all contending to want to go into the same slot. So that's obviously the downside of a direct map cache. If you have a lot of access patterns on your disk that all just so happen to have the same least significant byte number of their track, and all these bits differ in some way, they're all going to contend and cause contention on the same slot. And we'll actually see that at the end of this video when we look and see what's happening. So anyway, so what are we doing here? We take the track I want, convert it to the slot, then we ask, hey, given that slot number, tell me what track is currently in there, okay? Now we hold on to this. I had to move this code around a little bit. This may seem illogical to do that, and then this, and then way down here, use it. But that happens sometime due to branching and stuff like that. So bear with me here. We're calculating this in advance so we can use it later. Obviously, we grab the D so I can use it here, okay? And what I'm doing here is, we've all seen this before. I'm going to grab the current value that's in the latch, the GPIO latch that controls the bank numbers and the printer and the SD card and stuff like that. I'm going to save the current copy. Remember, I'm saving the current copy. Here's where I save it, right at this entry point into this routine. Because at the very end, the very last thing I'm going to do before I return back to BDOS is restore the memory bank, the GPIO latch, to this saved value. Okay, so this is me like pushing it on the sack, so to speak. Okay, so I have a little special save area at the bottom of this file where I'm going to keep that. And then what do? I zero out the, what is this thing? Zero out the RAM bank bits. Oh yeah, this game with the ending with the FF. I talked about that last time to placate the compiler to shut up its warnings. Basically, I need to make sure that this is essentially ending it with 0F, so that the most significant 4 bits are 0. Then I'm going to OR it with D, which we already talked about a minute ago. That is this bit pattern here that I want to put into those 4 bits, okay? And then I'm going to store that in the output cache, which is different than this one. Okay, the reason I need to have a separate one up here is, and the reason I need to save it into the global and shared cache copy of the output latch value, is because if you remember, the SPI logic and the SD card logic uses this itself, because it too needs to be able to update the GPIO latch and restore it to its original value. Not because it's playing with the memory banks, but because it's playing with the SD card bits. So I need to make sure that stays satisfied, all right? So I have to have an extra copy that I use before I modify it and then save it so the SD card uses and it manipulates the machine and the memory when the correct bank has been selected, right? So I output that to the GPIO latch. We do some debugging that we can see while it runs if we want. We fall down into here. Now remember, HL still has the track number in it. That is the one that is in the current slot that represents the one and only place that the track that the read routine needs to get must go. Okay? So what do I got in here? A little reminder that the track number will be all ones if the slot is empty. And that refers to the return value of this function up here. We talked about that last time. It's impossible for it to be this if the CPM tracks have more than one sector in them, okay? And we have 4 sectors per track, therefore the track number can never go all the way up to FFFF, okay? It can only go up to a quarter of that, which is 3FFF, all right? So this sentinel value is a great thing that we can use as a flag, as opposed to like if I use 0. Because 0 is a perfectly legal track. It could confuse the logic in here, all right? That's why I chose to use this as our there's nothing here indicator, right? So what do I do here? I'm going to go ahead and grab the track number again. This time I'm going to put it into DE, and I'm going to subtract DE from HL. Now, the Z80 does not have a regular old subtract instruction that means, subtract DE from HL and store the difference in HL, right? It has a subtract with carry. And that means that this instruction says HL equals HL minus DE minus the carry flag. Now, what we want to do is make sure that it's just going to calculate HL minus DE. If you OR the accumulator with itself, the side effect will be that the carry flag will have been cleared, and therefore this calculates HL equals HL minus DE, or as I say, HL equals the track I got minus the track I want. If it is equal, the difference will be 0, and the Z flag will have been set, and I jump down to the read cache hit logic, which skips over all the SD card stuff and goes directly to grabbing the sector that I want out of the slot / track / SD card block. All 3 of those are the same in terms of size and stuff like that, right? So it'll go down there and just grab out of the data that we have out of the slot that we already have, okay? But if it's not the one we want, we have to fall down in here and we'll see some familiar logic. Here's some debugging where I remind myself that I have a cache miss. And I'm going to play the game we talked about before. This is why we have to make sure that this partition base number is hex 800. And that we have formatted our SD card accordingly so that this partition that holds our disk image starts in the same place that this code right here, that this code uses to adjust to figure out which SD card blocks map into our CPM track numbers, okay? And this is the only reason that we don't have multiple partitions and stuff like that on this system yet, because I have yet to, formally improve this code right here, okay? But that's why this is still here. It's a XXX comment. Whenever something's wonky in my code that I know about anyway, you should be able to see a XXX comment lingering around in there. If you just grep all my source for XXX, you'll find all my little notes that say, oh yeah, this is dubious, I know, but deal with it, okay? So, point is, if anything you do doesn't work or misbehaves, see if there's any comments in here that say, oh, by the way, this is a work in progress, and I'm disclosing that this could interfere with, reasonable people thinking logically, right? So this is an illogical leap you might have to make here. I'm just saying. All right, so we do have an add instruction that does not involve the carry. That allows us to add the DE register to the HL register, which is how we calculate, right? The SD card number and the driver that we are going to use that has the SD command 17, talked all about that before, needs 32-bit value for the SD number, SD block number, I should say, and it gets it from the stack, so I have to kind of fashion that up. We talked about that before. Then what am I doing down here? What I need to do that's different about the last version in the BIOS is the last version had one single buffer. You could think of it as a cache that has only one slot in it. But this one, obviously, as I've been talking about, has 256 slots. So we have to go back to the track number, convert it into a slot number. Then I can convert the slot number into an address. We talked about that last time, too. This function here does this part of the mapping, right? So given a slot number here, give me this value here. And this is the address of the very first byte of the slot in the RAM bank where the data has to go, right? So what we're doing here is calculating the target address where we want the SD routines to put the block from the stack when it reads it into the memory. So I need to put that in the DE register. There's no way to get in there directly, so I do it one byte at a time. I then have some debugging here to tell me what I'm doing. I then go get the data from the SD card, given all the code. We never modified that since last time I talked about it. Clean up the 32-bit value off the stack, then ask if it worked okay. It returns a 0 from command 17 up here if it went well. If it did, I go down here to the read OK logic. If it did not go okay, I log a little message here. And I need to prepare to return to the BDOS with the correct value in the accumulated, a flag that a failure has happened. Okay? Now, just like before, when I marked my one slot buffer as dirty or invalid, don't use this because I don't know what's there kind of attitude, right? Because if you think about it, if this routine up here fails, all I get is a binary value, a Boolean yes, no. I don't know if there were side effects. Maybe it read part of it. Maybe it actually read it all and then got some other kind of an error back from the SD card. This may have corrupted, in other words, the buffer that is our slot that we're reading into. So if the read has failed, I'm going to reach over and again, use the routines we talked about before, and I'm going to store the tag invalid value into our into the cache tag, okay? By using the set tag routine. Again, I talked about that last time. So this thing invalidates the slot that we tried to read into in our cache because we have no idea what side effects there could be after a failure, all right? So we do that. We set the flag we need to set, and then we jump down to the BIOS read return. At the bottom of this entire thing, we'll talk about that later. If it worked okay, we also have to call the set routine, the set tag routine. And I mean, think about it, right? We wouldn't be here if the track we wanted was already in our cache. So we have a 100% guarantee that the track we just read in is not the one that was in the slot. Okay? So we have to make sure that we update our tag to remember which of the 64 possible tracks could be in that slot. So again, I'm going to grab the track number into HL and I'm going to call set tag. And what set tag wants, it wants the slot number in L over here. And it wants the tag value in H. So by putting the track number as a whole into the HL register and not really doing anything with it and just simply saying set tag, please, I wrote the set tag routine with this exactly in mind. so that the L value here is the slot number in this table that needs to be set to this value here, okay? And because we know that no matter what, the track will always have 2 0 bits over here, what we're doing is we're saying store these bits here into our tag table in slot number here, okay? And because these 2 bits are always going to be 0, that means that the invalid bit is off. This is always 0 anyway, it's unused. And that the proper bits here that represent the upper, byte of the track number are stored in the tag table. That's exactly what we want in there. All right, so that's a simple thing to do. We throw some debug on there to let us know that we did that. And here's the old slot number and the tag and all that other fun stuff. And then what do? We've seen this code, most of this code before. Now remember that this thing can be entered from the beginning of the read routine if we determine that the track we want is already in our cache. In addition to just simply falling down in here, in the case where it wasn't, where the track was not already in our cache, we had to read it in, okay? So no matter what, we need to figure out where the slot address is, add the offset to the sector within that track that we want to get to the address of our slot, right? And so I have a little comment over here. Add HL now equals the address of the CPM sector in the cache that we want to read, okay? Again, a little debugging to print that out, double check, and to make sure the code all works, right? And now I have to deal with this problem with the bounce buffer, okay? So what are we going to do here? We're going to say top level view, copy the sector data from our cache slot to the DMA address that the BDOS tells us that we want to put in it, right? So what I need to do is ask if the DMA address is greater than this, right? If it is, I'm in the upper half of memory, and I know that that's not, rebankable, so to speak, right? And if it is, I can just copy it directly from the low RAM bank that's currently selected, still selected, I should say, that's in our cache. And I can copy it right into where the DMA says. But if it's not there, then it means that what I need to do is copy from one of the banks that holds our slot data to the low RAM of the CPM memory, like in the TPA or this IO buffer over here. And because I can only select one of these at a time, what I need to do is copy data. Let's say it's in bank 2. I need to copy it way up here to a bounce buffer up high in the BDOS. And when I'm done with that, I can then switch the banks around and then copy it from the BDOS back down to where it's got to go, which in this case is always going to end up being bank 14 because the BDOS doesn't know about these other banks, right? So if it's above hex 8000, we can copy it direct. If it's below, we copy it up there, switch the bank, come back down. And that's what the code does right in here, okay? So if it's good, we go down below to read direct. If it's not, what we do is we say, okay, forget where the BDOS wants it, copy it into our bounce buffer. And we'll see later, this is just a buffer that's defined right in this file at the end of it. We know that this file becomes part of the BIOS, therefore we know by definition it must be over hex 8000, and it's perfectly legal to do this. We don't even have to ask, okay? So if we decide to use a bounce buffer, I throw some debug up there that says, we're using a bounce buffer, right? And then I play my LDIR game for hex 80, which is 128 in decimal bytes, from the address that we calculated way up here in HL, right? Which is where our sector data is in the cache, to the DE register address, which right now would be our bounce buffer. And that's the first leap, okay? Now, we come down here and we say, now that we've taken it out of our cache bank, we can switch the bank back to, and this is where we saved our special original GPIO latch, value, and restore that, which puts us presumably back to where the low bank is set to number 14 here for the TPA. Okay, We don't care what bank we're targeting. It doesn't know nor care. Normally, it would be this one. But this code is written so that if somebody decides to read in data and they need it bounced into bank number 10, for example, this will still work. I'm just saying, okay? So what are we doing here? We put the bank back to normal, or to the original setting. We say HL, which is the source address of our block copy, right, to the bounce buffer, because that's where the data is right now. The destination then is where the BDOS says it wants the data to go. I debug a little message here saying, by the way, the second half of the bounce is going to now go from the bounce buffer to the DMA target address. And I fall down into here, which is where we branched originally, if we did not need the bounce buffer, where I wrap up another LDIR block move there. So this will either finish the move from our bounce buffer, or if you go back and look up here when we asked, do I need the bounce buffer or not in the first place? Where is that? It's right here, in fact. At this point in time, the DE registers is as the correct DMA address, and HL, as you recall, at that point also has the original sector address that is in our cache bank, okay? So if we make this leap here, think about it for a minute, and we go into here, this will do the LDIR directly out of our cache bank up into the high memory, because that's what happens if we make that branch above. Or if we fall into this, we will have already swapped the bank back into the low bank, and we will complete the second half of copying it from the bounce buffer into, in that scenario, the low bank, okay? We set the accumulator to 0 to let the BDOS know everything went well, and we fall into this return logic, which is the same place we go, remember, when the read has failed and we invalidated the cache and set A to 1, right? So this logic here has to work whether we fall in here or warp into it from above. So I have to make sure that I reset the GPIO output port, because it may or may not be set back to the original value, okay? And again, I print out a debug message because I need to make sure that we, all our I's are dotted and T's are crossed. We're swapping banks, doing crazy stuff here. This could easily crash if we don't get it perfect, right? And then I clean up my stack from the main entry point to begin with. And what do I do here? I also swap the cache back. We talked about this before. This is the restoration of stop using our local private stack and go back to the one that was in use when this was originally called, and we return to the caller, okay? Now, go ahead and compile this thing up. And we program our flash card, put it back in the retro, hit the reset button, and let the debug spew. We looked at the debug last time. We didn't look too closely at what happens for all the extra debug in the middle of the read routine that we just looked at right now. So let's take a quick skim here, because the real value here, in my opinion, is when you hit the escape key and you can dump out the tag table while it's going. So we can see that this is the time now. Is it about 8:50? Yeah, it's about 8:15 in the morning, 8:19 in the morning. It's a nice way to spend a beautiful Saturday morning before breakfast, to sneak down here and get a little coding in. Anyway, what do we got here? So it's sending us the notice to make sure we get the right version of our configuration, and we watch it when it boots up. As you recall, it reads in all the tracks from the directory one at a time to build its allocation vector. So again, I think we looked at this last time. Every time we read in the first sector of a track as we scan through the directory, it's a cache miss, which we now know is going to look like this. And it says, look, the current tag is invalid because the most significant bit is set there. The new tag should be 0. And the reason the new tag is 0 is because the track number that we want is 00, which is our tag number, 20, which is our slot number. And you can see their slot is 20, and the tag is supposed to be 0. Current value is invalid, and we read it in, and you can see all the extra debugging that we just looked at, kind of skimmed over in the read routine going on here, and the notion of I'm doing this and I'm restoring the bank when I'm done because it switched it over to bank 0 and now it puts it back to 14 and all that fun stuff, right? The second time it comes in to read a sector, of course, it says I again want something from slot 20 because it's on the same track even though the sector number advanced, right, from 0 to 1. But this time it finds out that in cache slot 20, the current tag is 0, which is exactly what we want. So now it says, yay, it's what I want, cache hit, yes, and we don't see all the read logic down here debugging itself out like we did up here, and that's a cache hit. So we got 1 miss followed by 3 hits, and yay, I'm super excited. I mean, we talked about this before. That worked great even when we had a 1-slot cache, right? So right now, we just booted up our system, and right now everything is reset. So this is actually going to run the exact same performance that we had before with our 1-slot cache, because we're marching through the surface of the disk, 1 sector at a time. So yes, it'll find that the first sector on each track, now that we go up to 21, is going to be invalid, followed by, okay, good, I got what I want, times 3, and then a bad one, and a good, bad, good, bad, good, all the way to the end, okay? And if I hit escape, because I have my debug wedge turned on here, I'll backspace a little bit to get the escape character out of there that you saw come through here so I don't accidentally then type that into CPM, right? Anyway, so I can see the tag table debugged here, and this is exactly what we would expect because it read in track number 0020 through 003F. Okay? In the 00, left's most significant byte of the track number is essentially the value in the tag table, unless the most significant bit is 1, which is the case down here and up there. And I explained before, while I use FF so that I can easily see it in my debug output, rather than simply setting it to 80, which is, of course, also a perfectly valid way to invalidate a slot in our cache. This is just a lot easier to see. Now, while it's going, I can run commands like directory. So let's look and see what this mess is really telling us, all right? So now we can really get into the testing of this. If we type dir, remember it's going to go back and read the directory, print the stuff out. So what is it going to do? It's going to say, I want to read what sector 0 on track 20. Not shocking. It goes back and reads the first sector of the directory, and then down here you'll see it reading what? The second sector somewhere. If we look at the debugging output here, actually, I think we have a problem here. I need to turn on line wrapping, which is a little bit annoying. That's off by default. Let me redo the directory command here, because I think that this, yeah, the line, I think, wrapped around the screen in a weird way and made it hard to read. Yes, that does appear to be the case. Okay, so first time it goes through, it wants to read what? Sector 0 on track 20, and it comes up and says, okay, here's what I want. And it's in our cache. Now, last time, the prior release of the BIOS, this would not have happened, because prior to doing this directory command, remember, it will have just finished scanning the disk. And if we only had 1 slot, track 3F over here would be sitting in that slot. But now, we don't have to go back and actually read, because we have track 20, track 21, 22, and all these other tracks, all the way up to 3F, are still in our cache, right? Because here they all are in the tag table. We have 32 tracks sitting in there out of the 256 total. So the entire directory is sitting in RAM right now. So no matter what I do in the directory, it'll never have to go back and access the SD card again. In fact, if you watch the card go while you're hitting DIR, you'll see that the activity light on the SD card never lights up at this point. You can type DIR as many times as you want, and the SD activity light will never turn back on, because we're running entirely out of our cache at this time. Yay! So here's our first real improvement in performance, okay? Now, let's look some more about what's going on and kind of how the cache works to make sure everybody understands. I've typed dir multiple times. It's using the data out of these tracks over and over again. That's exciting, okay? Now, I happen to know that when we format the file system using the simple tools on the Raspberry Pi, like I've been doing all along, what it does is it puts the files on the disk file system image in the order that I give them on the command line when I say, here, copy these files, okay? The simple file system, the makefs.cpm command that we use, also puts all the data in the data part of the disk on the disk as it goes along. Therefore, asm.com, whatever data blocks that file uses on the disk, will sit here. If we find where's our debug output again from the escape key? It turns out that I can guarantee you that asm.com, for however many tracks worth of data it needs, will be starting right here after the directory, okay? Then the bios.asm file, for however many tracks worth of data it has, will be on the tracks following asm.com, all right? Now, that's not normally the image of a disk will, fragment over time and it could end up all over the place. But this is a handy thing to keep in mind right now, because if I say type bios.asm, we're going to see a lot of spew because it's going to go out and read the data, sectors for this file while it's printing it on the screen. And we'll also see all the output of the bios.asm file. What I probably should have done is done a pip and sent it to a non-existent printer so that it's not as noisy. Maybe we should do that. But before we do that, let's go ahead and hit escape anyway, because just to prove the point, to make the point I'm trying to make. Look what happens here in our cache. Before, we had zeros here, through there, and FFFF everywhere down here and up there, okay? Now, after I've done this type command, look what we got. All of these tracks here must contain the data that I just listed on the screen from bios.asm, so that's all now sitting in my cache. Bios.asm is a fairly large file, I guess. Keep in mind that each one of these tracks is a half a K. So by saying here's 16 of them, that's 8K, plus half again as much, plus 4K is 12K, or less, because this last one might not be entirely used. Okay? So if we do a stat, well, actually, we don't want to do a stat just yet, because if I do stat, it'll mess around with this even more. I was going to say let's do a stat to see how big these files are and confirm all this. We'll do that in a minute. Let's go back and look at the directory again, though, first. What did I want to do? I wanted to do a pip, and that's going to mess with it as well, because pip is sitting over here. Also would have to be read in off the disk in order to run, okay? So keep in mind what we're doing and in what order here. So we have asm.com. We did a type on this, so that was read into our cache. If we run a command like stat, which is, where is it? It's like way down here, okay? What'll happen is this data on the disk for that COM file will have to be read in, loaded into the DPA, and then executed. Then while this is executing, it too could do disk I/O, and in fact it does. It will read the directory, but it won't read anything else because that's what the stat command will do if I run it. But notice also there's a README file right here that comes before the stat.com. And again, I know that these are stored in order on disk, unfragmented, end-to-end, in an orderly fashion, because we have not yet modified any contents that is on our disk. So the point is we can figure out where stat.com actually is by doing a type on the README file, as long as we pay attention to what the tag table looks like before and after we do that type command. And I know the README file is super tiny. So there you go. It basically is this, 2 lines of text, all right? So let's now go back and take another look at the tag table. Lo and behold, this guy miraculously got read in, okay? This is the 1 track's worth of data that is in the README file. So we can also confirm that by looking up here. What's going on? It reads this, it's going to go back and scan the directory to find out where the README file data is on our disk. This is it scanning through the directory. Where is the README file, please? It finally gets down here. It must be in the 4th sector on the disk, okay? That is the entry that says here's where the README file data is. In fact, we can figure that out by scrolling back to the directory and count. Well, it debugs here, right? Where is the README? It's sitting down here. Well, that is the line that's printed as a result of this read right there, okay? And that is 1, 2, 3. It'll be the 4th one. Here's the first one, the second one, the third one, and the 4th read of the directory that resulted in it saying, here's a file called README. So we know that when we execute the type command, it has to find it, and it's scanned up to the 4th one, and it stopped, because there's obviously more directory entries, but once you found it, why keep looking, right? It's always in the last place you look, because who would keep looking? All right, so moving on. Once it has found the README entry on the directory, it knows then, because that's what's stored in the directory, the track number and the sector numbers where the data is located for the README file. So what happens here? Now we get some interesting stuff going on. This track number is pretty big. It's E4 now. So now we're in bank 30 instead of bank 0, right? The address in that bank is based on bank 3, I should say, instead of bank 0, which is 4800. And what are we doing here? It's a miss because we've never seen that before, and that'll make sense. And we see it actually do the I/O, and we switch the slot, and we switch it back, and then we print out the data that was in there. In this case, you see it using the bounce buffer, okay? Didn't use the bounce buffer up here before at all, and the reason is because when we read the directory, the DMA addresses were always this high value. These are the directory buffers that are in the end of the BIOS area. That's part of the disk parameter block and all that we talked about long ago. Okay? Now, it's not until you actually start, actually, if you look closely, I'm sure it used bounce buffers here too, because the type command has to store the data somewhere when it prints out a file. And if you watch it go, I'll bet it uses address 80. It does, because that's the default buffer address that you can use for general I/O, and that's what the CP/M BDOS does as well. So this time we would expect it to use the bounce buffer, and thank God it worked. Otherwise the whole thing had come down like a house of cards. So let's see what's going on here. What do? We see the cache slot address is the one that we calculated and printed out up here in the debug routine we talked about last time. We have the current tag is 0. No, that's the new tag is supposed to be 0. The current one is FF. Therefore, it says this means update the tag to the value 0 for slot number E4, because that's the slot number, and this is the, and this over here, remember, becomes the tag. And this is all nice and simple because we've yet to access a track greater than FF, okay, but we're getting close. In this case, we're all the way up to E4. Okay, so you see it use the bounce buffer, and what does it do? The bounce destination is F006, and then it says, and here it would have switched the RAM banks and say, this is the second half, so now it's bouncing from F006 down to 80, and when it's done, it redundantly, in this case, would have restored the bank, because we already did that while doing the bounce, right? And of course, once the disk sector is in the buffer, the BDOS can print out the contents. In other words, execute the type command. All right, so there's E4, and that all makes sense, right? Okay, so let's go ahead and do another directory because I forgot what's where. And we just looked at the README file right here. Now it gets interesting. If I want to run the stat command, and that's what we've been waiting for here. We found where the sectors must be, or the tracks must be, that hold the executable image of the stat command. it must come after the README file. Okay? Now, remember back to our disk parameter block. If this is the contents of the README file, remember that's a whole track right there. And when we did a type on README, it only needed to read one single sector because the contents of that file is tiny. It's just this. Okay? It's only not even a whole sector. And we'll see more about that when we run the stat command. It'll tell us how many bytes are in the file. Okay? Or how many sectors anyway. We know, therefore, or will confirm the fact that the README file is a single sector's worth of data. Even though we have to allocate at least a whole track in our file system. Now, not only that, we have to take it one step further. In our disk parameter block for this file system, you might recall, is what I did was specify that all files have an allocation block size of 2K. Therefore, all of these tracks have been allocated to hold the contents of that README file, whether we use them or not, because the minimum allocation block size for any given file is 2K. Therefore, what will happen is, I hope I'm right, I'm just winging it here, people, is that the stat command blocks are going to start right here. Okay? So let's run the stat command. Stat star. And what this is going to do is read, oops, if I type it in right, it's going to read in the directory and spew debug all over the place. Then it's going to sort all the names of the files and print out a nice table that says, here's how big everything is. And it's a little bit unfortunate right now that it actually sorts them alphabetically, because it'd be nice, and maybe there's an option for that. I look forward to your comments below. Anyway, it'd be nice if it was not sorted and it was printed out in physical order, and it includes things like, which track numbers and stuff like that, so we can see what's going on. But this is still very useful because we know what's really happening here, right? So what do we know? The README file says it has a 2K allocation because our allocation block size is 2K, and that only one record, I don't know why they didn't call it sector, but one sector / record / 128 bytes in decimal or 80 in hex bytes has been used to hold data for that file, which is exactly what we just saw when we dumped out our tag buffer, okay? Now, lucky me, I was right. the stat command came right after the README. So these here, all these zeros, will make sense if you go back and if we evaluate all this stuff in here. What you'll see is it'll be reading sector E8, E9, E8. In fact, there it is. You see the E8 and so on. Starting up here, when I typed in the command, which it overwrote with debugging spew, it's going to scan the directory looking for the stat command. Then it will start reading the stat command's data, which we just saw had to start at E8. And it goes one sector at a time in order. And you see it does a cache miss, followed by 3 hits, followed by a cache miss, followed by 3 hits, because it's all stored in order because the disk is not yet fragmented. We got another miss, followed by some hits, and so on. And we see it 8, 9, A, B, and it'll go to F something, right? Because it went around to like F 2 or 3 or 4 or something like that. There's F0, F1, right? It keeps going here. There is F2. Now there's a space here. And I think that what CPM does is when it loads a program, it prints a carriage return. So that's what this is. That's CPM printing that before it starts the program running. Now the program starts running, which is very handy that they do that for us. Thank you very much. The program starts running, and what does stat do? It reads in the whole directory. Again, we have all cache hits because the directory is still in our cache, right? So this actually would run much faster, especially if we didn't have all the debugging on, than it would if it had to actually go back and read it from the disk. And even more so if you have real live floppy disks, which everything just takes forever to keep moving the head around and reading and all the stuff. Okay? So we've got all the way down here to readme and stat.com. These other files down here, I guess we could print this out or something. What do we know, though, right? We know that actually these are not necessarily after the stat.com because it's sort of the directory, right? Let's do this again. What is after stat.com? Physically on the disk is submit xsub, and then our adventure program and stuff like that. Okay? Now, if stat.com are these tracks here, then we know for an absolute fact that submit, which is the file that comes after it, is at least this allocation block if it has any data on the disk at all. And submit, is right here. It has 10. It has one allocation block associated with it. Then symbol tab. I think these are in alphabetical order, so it's coincidental that the stat command will do the right thing. Stat, submit, and xsub are in that order. Stat, submit, symbol, and xsub. So we got 2K, 16K, and 2K if they really are in that order. Stat, submit, xsub. Yes, okay. So what would happen is, what did I say? We got 2K for this. So if we were to run or somehow open and read the contents of this file, it would start and use these tracks. Symbol table needs 16K, right? Well, this is 1K. 16K is 2 whole lines on this dump of tags. So symbol tab would start here and most likely run all the way around to track 100, and that would be 1 row, 2 rows, and it would end here. So it would consume all these tracks, wrap around, and start overwriting. Okay? Xsub probably starts here, and it's only 2K, so it would be this. Okay? So what comes after xsub physically on the disk is adventure.com. Now, adventure.com is a pretty big file, and it has all these data files that goes along with it, all these AVT files. So if I was to run it, it's going to want to read like 288 records. This thing is bigger than our entire oh, no. Those are sectors, not tracks. This is 36K, which would be 64, or actually like 72 tracks, because each track is a half a K. So you take the number of kilos, double it, right? This uses 3 directory extents, for crying out loud, to hold all that data. So if I run adv.com, I have to read in 64 tracks, assuming the entire file's read in, and I'm sure it is when you load it. And they probably start here, okay? Which have tracks that, like I said, it would be track 1C is probably the first track of the adventure program. And if it reads in 64 of them, that's half this table. So if we read in adventure, we should see a bunch of cache misses, and we'll see misses because these tracks represent invalid slots, and we'll then see it clobbering the cached copies of all the directory entries and the README file and the bios.asm. All these files that we read into this cache will have to be written over again. And that's the nature of a cache, okay? So if we run adventure, let's see what happens. Lots of reading. Okay, there's the 64 tracks, right? Times 4 for the number of sectors. So this might spew a little while to load up the program. And then it asks, do you want help or something like that, right? See all these new tag 1 as it scrolls by. And some of the, and now we actually get all the way up to new tag equals 2, for crying out loud. And the reason that happens is because not only does adventure load and then start running, here's our blank line, I assume. This might be the end of reading. Oh no, this is like say news. Oh my gosh, so here's the copyright. So yeah, adventure starts running way up here somewhere. Maybe the copyright's the first thing it prints out. We can sort of figure that out based on earlier reasoning. Track 21. Oh, there's it reading the directory. Just coincidence that we ran into track 20 here. Here's something that's crazy. Track 16E. This is probably near the end of the COM file. If it uses half the cache. Actually, if it uses 64 tracks, that's not half, that's a quarter of our cache. I'm sorry, I miscalculated in my head. And that would come out around, at or around 16E. So this is probably the end of the COM file that then goes back and wants to read the directory again. Or this is the BDOS looking for the next extent. Because remember, it said that this thing had 3 extents, which means that if you don't know what an extent is, or an extent, or whatever, however you want to say it, it means that the file data cannot all fit in one directory entry. So more and more directory entries are used to say this is a continuation of the prior directory entry that has more data for the, in this case, the adventure program. So somebody has to go back into the directory and read it again when that happens. And that might be what's going on here. I don't know. We'll see. Now we warp way up here into 229. Notice the DMA address now is 8FD5. Well, what the heck is that, right? Most likely, that's where Adventure has its own data buffer. Now, purely by coincidence, that's over the 8,000 line, which is really handy. We don't have to use a bounce buffer, even for while Adventure is running. That's pretty cool. I never noticed that before. Anyway, so you can sort of see what's going on. You see the code's working. You can add additional debugging output if you want. A lot of the debugging that's in the low-level library routines we looked at before is disabled because it's just that'll more than double the amount in here. But if you really want to see what's going on, turn on all that fun stuff and see what's going on. So what do we got in the end of it? We know we're in the console input routine, so we can dump out the tag table again. And we can see all sorts of stuff that's going on here that's kind of neat. So what is going on? And we'll see all these O2s in here. And we see these O1s, then we see OOs, invalid ones here, and then we see more O1s. You'll see this thing is starting to get filled up with random stuff all over the place. There's an O1 out of nowhere down here. What's going on here? Well, it's getting late in the morning to walk through every little debug statement in here. But what you'll probably see if you scan through here, when Adventure is running, it's reaching out and interacting with its data files. Here's track 1D0. Here's track 229. So what did it do? It read in, here's 1D1. So it says, welcome to Adventure. When Adventure is running, it's interacting with the disk. It's reading track 229, 1D1. What's going on down here? Track number 1D0. So it's jumping all over the place. Okay, here's a 229, 22C, 1DB. So you would expect it to have read, you'd see a lot of things that have O2s because the track numbers start with O2, and that would go into 2C. When this thing ran here, it would be an O2 and then a 2C, which is right here. This one's set to O2 right now because of this debugging right there. And here's a O1DB with a hit equals no. So this is it reading in track O1DB into slot DB. So we look at DB. Where's D? See D, 9AB. This is C. What is that right? Oh, this is 89AB. I'm embarrassed. I need more coffee. Wow. Yeah, of course, this is column 8. Okay, fine. I look forward to your comments below. All right. So the point is, it appears that our read routine is working correctly, and we're updating our cache tags appropriately, and everything's working as we expect it to. Next time, we'll take another look at the write routine so that we can release this and use it as our standard go-to. Now, there's one last thing I wanted to make sure that I point out, and that's this. I said it's near the bottom of the file. If we hit Control-G, I'm in BI, so I'm all the way down to the bottom of the file at 91% mark. Before we saw this, there's the init routine that we use to clear out the cache of our tags and so on. This is where the bounce buffer is, and this is where the GPIO extra storage area is, right? So that's where those are, just so you know. And here's the old write routine. Again, this is still stubbed out. If anybody ever tries to write into the disk, this will return an error and ignore it. Okay? So next time I'll try to write this routine. Should go a little bit faster, because all that has to happen in here is, again, the same sort of thing we did before. Replace the single slot logic with our cache logic. And the interesting thing about the write routine is we have to read before we write, or so we said pre-read, because it might want to write a single sector into the middle of a track that's not already in our cache. Same problem we had before, but we'll outfit this in the same way we did the read logic above. And so all we're really going to end up doing is expanding the simple logic in here, where we invalidate the buffer with the 4 or 5 lines it takes to invalidate the slot in our new cache, right? Thanks again for all my viewers and Patreons. This is a lot of fun for me, and I'm glad to know that it's fun for others as well. Thanks for watching. See you next time.